This is Amirhossein.
And this is Milad.
We are researchers at Mila, and this video is going to be about nanoAhaMoment, which is a single file, single GPU, very efficient recreation of R1-Zero like training from scratch. So we are not going to use any library, any other library, and we are going to show you how to implement this in training style in a very efficient manner. We are going to use a 3 billion base model in full parameter tuning with single GPU. And this entire thing is going to only take less than 10 hours to finish.
Why do we need another script for recreating R1? There are already some scripts out there, but the problem with most of them is either they are importing their trainer from TRL library, for example, so their code is not a single file. They are importing it from other places, so the code is not hackable and sometimes even not efficient. But also, the efficient code bases are mostly based on Ray, for example, the VERL code base. We think it's more useful maybe for industrial applications, but not that useful for academic purposes because it is unnecessarily complicated. Because the Ray system handles multiple nodes, failure of jobs, but when you just have a single GPU, none of those problems are going to occur, but you're going to deal with the complexity of the framework.
Yes, and honestly, those libraries, they exist for a good reason because as you're going to see, the efficient RL training, efficient RL experiment is going to depend on two main components, efficient training and really fast inference. And having these together work seamlessly in their maximum potential, it's going to be quite challenging to implement, and it's going to require few optimization tricks to create. These libraries, they unfortunately have to be this complex to handle all of these cases. However, in this video and in this code base, we are going to show most of these most impactful tricks and most of these optimization style, the coding styles for auto training. In this video, you are going to also learn these different ways people try to integrate these two main components of auto training. I think this video is going to also be a very good training resource for people who are interested in auto training of LLMs.
So what we're going to do is we take the Quen 2.5, the 3 billion base model, the pre-trained model, and we train it on the countdown task, which is, I think, popularized by the TinyZero code base. The task is you're given 4 numbers and you need to provide a mathematical equation that results in a target number. And the model needs to try different approaches to solve this problem. That's why reasoning suits this problem. And we're going to train it with GRPO. And let's see what we will have and achieve at the end of this video.
So as you can see, we are going to train a model that at the end of the day, it's reproduce the aha moment or these kind of interesting patterns that kind of emerges during pure auto training on a pre-trained base model. Basically the self-reflection, self-verification, backtracking, and so on. As you can see here, the model says, let me try something different. And it says, wait, I think I'm getting there. So as you can see, all of these patterns that you have probably seen in actual R1 models or any of these reasoning models, you're going to actually recreate these in a kind of a single file, not full from scratch. And on the left, we have the kind of the average response length, which is at this point a famous response length plot that we have seen for this kind of training style. And during the first few iterations, the model is going to fine-tune its generations to follow the format and just get the hand of a task. And after a while, it's going to use its thinking budgets or thinking tokens to actually improve its model's question-solving ability or its reasoning ability. And that's why probably we see this pattern. And we are going to see what would really happen at the end of a training where we have very long responses at the end of this video. The goal of this video is to go over this code. We are going to start with this clean slate, literally clean file, and we are going to implement all of this from scratch together. And we tried really to make sure we include every little detail that we know and that are actually useful for this video. It's gonna be one of those few hours tutorials, Carpaccio style, And I hope you guys learned something and enjoyed this video.
Yeah, it's going to be quite long. Actually, we are recording this after recording the whole stuff, and we know it's going to be long. So we hope it's useful for you. We think it is. And let's start.
Okay, so before diving into the implementation details and all of the code for R1-Zero training, I would like to first go over the actual the training recipe, just to make sure that everybody watching the video is on the same page. Okay, R1-Zero recipe is actually quite simple, and I think that's what makes it quite scalable and powerful. And the zero variant of R1, basically it starts from the pre-trained model. It is right out of the pre-training stage of LLMs. And you do not apply any instruction tuning, no supervised fine tuning on this LLM, and just use it as is. So once you have that, you use a thinking prompt, and you basically append your problem definition to that thinking prompt and just feed it to the LLM. And you let the LLM generate your reasoning, generate its response. And as you're going to see, you're going to force the LLM to first think and then produce the final answer. Once you have this response and once you extract the final answer, you're going to use the verifiable reward to compare or check the correctness of the model's output. So what is verifiable rewards? Basically, it checks the output of the model, the answer provided by the model, towards against some ground truths that you know that is the answer of this question. So basically, it can create for you a binary reward such as 0 or 1. And once you have that, you can use a GRPO, or in general, it is very simple modification on top of reinforce, and use that to update your policy. And these three that you can see here are three different components of the notebook or the implementation that you're going to see today. And these three components, once coupled together, they're going to constitute our training loop for R1-Zero training. And if you want to learn more about what is R1 or what is R1-Zero, if you want to learn more information about this, there is a great video by Sasha Rush, and he talks about all the details, all the backstory story, how R1-Zero created, the base model, and all of the innovation that is involved in it.
But can I ask, what is the significance of R1? What part of this pipeline was unknown before we have the DeepSeek R1-Zero paper?
This is, you're starting from a base pre-trained model, and there is no human supervision here. And your pre-trained stage is totally unsupervised, and your RL stage is also almost unsupervised. You're going to need to know the ground truths for all of these reasoning problems, these mathematical problems. But in general, you're not going to force any thinking patterns inside the model in the model. And I think letting the model to discover what is the best way to solve these things, these types of questions by itself, is quite exciting.
So I guess like previously they needed to induce this human thought process by instruction tuning, but currently RL picks up the signal from the pre-training model itself.
Yes. After OpenAI O1, there were many efforts by folks in the research community to reproduce O1, and many of them involved these kind of inductive biases that were forced to the model. But R1-Zero, it doesn't require any inductive bias, and the training is done without any human supervision.
I see. So the simplest approach actually worked.
Yes. We actually thought before going into the code implementation, it would be better to just show you the final result of this entire video and this entire training, and just let us play with it a bit and see how it performs and how it looks like. Okay, so we have uploaded the model in Hugging Face into this repository, nanoAhaMoment 3 billion, which is based on the Quant 3 billion base, and we just exactly train it with the same task, the same file. And
it's a final checkpoint, right?
It is the final checkpoint of one of this run, the run that you're going to see. Okay, let's run this, and click here that we can play with the model. Just load the LLM with this. Let's just play with the model. So we have right now an easy-ish example here. So we have 1, 2, 3, 4, and the target is to create 10. So the model just has to sum this up. So as you can see, The model is just thinking smoothly, start with the largest number, adds all of these together, and it reaches 10. This one
It was too easy for the model.
too easy for the model. Okay, here's another example. Let's see how the model works. And it says starting with the largest number again, and it also try another order here, and it seems that it has found the answer. Let's just check this. 64.
Oh, interesting. Did it? Yeah. Oh,
Beautiful. Here's another one. This should be slightly harder. Let's see how does the model perform. So this is the output. Oh, the model just gave up.
yeah. Cannot solve.
Let's see. 66.
No.
And this is the model that you're going to create at the end of this tutorial. But like, I want to close this off with an interesting example. Here we just pass the inputs, like the problem formats that the model just saw during training, exactly IAD. But now the question is that what would the model do if you pass a non-countdown example to the
Just
model?
like general question.
General question.
From a
general
checkpoint that is trained
right?
on. Yeah. RL trained on like countdown test.
Right. Because this, as I said, this entire checkpoint that we are seeing right now, it was only trained, it started from pre-trained model and was only trained on countdown task with the verifiable reward, that's just checking the final answer, and also the format. Now the question is, how does it perform?
What do you expect actually?
If you pass a generic prompt? Honestly, I think like my prediction is that it is going to try to mix in the answer to this question with the format or the thinking of countdown task. Maybe
it's the only thing that this has seen, right?
Yeah, that's my machine learning common sense.
Yeah.
So let's see how it works. So we just pass this as a prompt and say, how are you? Show your work inside this tag, and yeah, ended with these answer tags. And honestly, the answer is interesting. Before showing you this, we actually ran this example and we were surprised to see this, that the model kind of says, start with initial greeting, hello, how are you? This is a common way to begin conversation. The person asking the question is likely looking for a response or to initiate a conversation. The question, how are you, is a polite way to inquire about someone's well-being. It's friendly and casual way to start a conversation. So it says, how are you? That's the final answer. And let's try to see.
This is present the greeting into its components. It's a common way to start the conversation. The greeting hello is a formal way of saying hi or hey. Oh,
it's beautiful.
Yeah. It's beautiful that the model, I don't know, it's a pre-trained model, and then you train it with RL on a completely like in a countdown task, and it reasons how to greet you.
I generated again, and this is an interesting response. We never said that this is an AI model,
but
have we?
Did
we have said that you're a helpful assistant, so maybe.
But well, I don't know.
I am functioning. I don't have feelings.
Yeah, and as I'm functioning normally. Interesting, functioning normally. The answer to hello, how are you? It's quite strange that the checkpoint is able to speak. Yeah.
In any case, I think this is quite interesting and hope you can also recreate this experiment yourself.
See you in the next parts.
Okay, now let's load this dataset from Hugging Face, the dataset for countdown task, and let's inspect a couple of examples together. Before doing that, I would like to set my Hugging Face home environment variable just to make sure that all of the downloads and all of the caches from Hugging Face is not going to blow up my home storage or whatever storage that you're going to use for this implementation. Let's get it started. Import OS just to set the environment variable, and let's import path. So now I'm going to define a global variable called scratch. This is going to be my home directory. I have this scratch folder inside home that is linked to my shared network storage. If anything that is saved here, it's not going to make any problem. And now let's define this environment variable to be something like this. Okay. Now that we have everything set up, let's load the dataset. Let's import the Hugging Face assets first. Dataset is equal to load dataset from this repository. This repository is actually created by the author of the TinyZero repository. Right? And we are going to use the train split of this. So yeah, let's load this. Perfect. We have this right now. And let's inspect one of these examples. I think, yeah, let's look at the last one.
500,000 almost.
Yes, we have 500,000 example questions like this. It is really easy to generate. So,
Yeah. Yes.
Okay, now we have this, as you can see, you have a set of input numbers or 4 numbers here. And you have to arrange this using the multiplication, addition, subtraction, and division to create this target number. And for this case, I encourage the viewers to pause the video and try to do this themselves. But here we are not going to do this manually, and we are going to use DeepSeek. And let's see if the model can solve this. I already have this in my clipboard. Let's pass this to DeepSeek.
Why have you not paused? Still, pause it.
Okay. I'm not sure how long this is going to take. If it's going to take more than a couple of seconds, we're going to cut the video. But for now, let's see.
I think it solved it.
Yeah, as you can see, I think it already solved it in this case. But as with R1 models, they're going to verify their answers a lot, maybe sometimes too much. And as you can see, it is still running. So probably I think it is finding a couple of different answers for this equation, for these numbers, but I don't know.
Maybe it is searching for the simplest looking one.
Maybe, but we didn't really specify this in the prompt. It has found a solution. This is the correct solution, right?
Let's verify this. Yeah, it's correct.
It's correct.
Is it? Wait, can you? Yeah.
It's correct. It is correct. Okay, now I want to go back to the R1 recipe. Okay, as you can see here, we are in the very first part of the implementation, and I want to implement and create the training prompt for oral training. So let's start with this part. Okay, so first of all, I'm going to define the prompts, the thinking prompt that we're going to use. So we're going to have a system message and a prompt template, which I copied before. And I'm going to briefly explain this to you. And this is similar to, I think we found these prompts from Mini R1-Zero codebase. These are not really particularly special prompts. It says that you're a helpful assistant. You first think about the reasoning process in the mind and then provide the user with the answer. And we also have the template that we are going to use. So basically, it is the problem definition that I showed you in the previous slide. So using the numbers, we are going to place the numbers here, create an equation that equals to the target number. You can use basic arithmetic operations, and each number can only be used once. Show your work inside the think tags and return the final equation and answer in the answer tags. For example, here is one example that the model can use. And yes, so this is the kind of the system, the thinking prompt part of the code.
But the model is not trained to follow any instruction.
Yes, exactly. So the model is not trained to follow any instruction. It is a base pre-trained model. And the notion of system message, it doesn't mean anything for it. So we are going to use the system message anyway to just make sure our entire pipeline and the final output of our training is compatible with the other tools and
chat template of
yes, that require or expect chat template or chat models. But anyway, this is not part of R1-Zero recipe in any way. Okay, so we have this prompt message from template here. And now I want to implement the pre-processing of the dataset. I want to create a proper prompt and feeding the model with this. By the way, we realized that in the previous thing that we copy pasted here, there was
They told us if you put a mistake in the video, the viewers are going to attend to it. Like it increases attention span.
Yes. So we fix this mistake here. Okay, let's get this started. So first I want to load the tokenizer. Just before, let me define the model name. I think this is going to be Quan 2.53 billion. Yes, I think we need to also pass the repository, right? And the chat name of this is going to be model name plus instruct. And also, let's not forget the dash. Okay, now let me load the tokenizer. This is from Hugging Face. Okay, perfect. Yes. And just I want to mention here, we are loading the chat version of this tokenizer. There is almost no difference between the chat tokenizer and the base model tokenizer. However, there is a small difference in the end of sentence token that we are going to fix that problem later. But for now, because we are going to use this system prod and system message and these kind of chat templates, we are going to use the chat tokenizer of Quan. Okay, now we have this. Let me rewrite. I'm going to use Hugging Face dataset map to pre-process this dataset and convert it to the chat format of the model. Okay. So this is the function that is going to perform the formatting for us. So the example is going to be a dictionary from string to any. Let's see if, yes, from typing import. Nice, okay. And the output is also the same dictionary. Okay. And let me extract these fields from the input example. I think this was noms, and target was also example target. Okay, so these are the inputs, and let me create the chat messages. This is going to be a list. So the first item is going to be the system message. So we set the role to be system, I think, and the content is going to be equal to system message. And the next one is going to be the actual prompt for the question. So the role is going to be user, and the content, on the other hand, is going to be called prompt template that we defined the few cells above. We are going to format them and say, I think numbers were equal to noms, right? And the target was equal to target. So just to make sure that we have everything under track, let me check numbers and target. So I think we're good. Just to make sure we are consistent, let me redefine this variable. Okay, for some reason this we're using parentheses. Let me convert it to brackets. Okay, so this is generally the chat message. This is the prompt that we are going to create for normal models. However, since we are starting from a base pre-trained model, the model by default may not follow these instructions, right? So it might as well continue the question, generate the rest of the question, right? And in order to prevent this, or actually maybe help the model to force it or make sure that it starts generating an answer or a response to a question, we're going to pre-fill the model context with the assistant, and let me think it step by step, just to make sure the model is going to respond to the prompt, not continue the prompt. Okay, so the role is going to be
But we never actually tested whether it's necessary, right?
We never tested
We never
it, to be
tested it.
honest.
So maybe it also
correct.
works. You don't know.
One of the things.
But it doesn't hurt.
It doesn't hurt, yeah. One of the many things that one could check.
Yeah, you can check it with playing with the code base.
Okay, so the content that I'm going to use is basically, let me think step by step. I don't think this has really any effect, but this is nice to have this prompt. And let's say like \n and start the think tag. So this is actually what R1 paper does as well. Even right now, if you look at the Hugging Face implementation of R1, these think tokens are appended to the kind of pre-filled to the prompt.
Do they have a R1 implementation?
They don't have R1 implementation. They have R1 implementation of their tokenizer.
Oh, I see.
If you load the tokenizer,
it
tokenizer
will add the
automatically
token.
this. Okay, I can actually show this to you. It's only the R1-Zero version, but I think even R1 itself, which is itself an instruct model, I think they have these things. So if we go here, load more files, still load more files, tokenizer config, they can load it here. And yes, so this is a chat template. It's not really readable at this point, but what I'm going to show you is here. So yes, a lot of components, but I think yes, as we can see, when it wants to just finish the prompt, it appends these two things. This is something that has been done by the original R1, and we are going to follow that as well. Okay, now let's continue the rest of the implementation. So next I'm going to tokenize this and also create the textual prompt, so for logging purposes. And yes, so I'm going to use the tokenizer. By the way, if you feel these parts are easy and they don't have anything interesting for you, feel free to skip a part. So we're going to use the tokenizer, apply chat template. We're going to pass the chat messages. And also we need to make sure it is going to tokenize it for us. By the way, this tokenizer, it is a global variable. Since we are in notebook, this is fine. And this is educational content. Don't use this, don't follow this pattern in your actual code bases. And I think, yes, and since we are pre-filling the assistant part of this, we have to enable this flag so that Hugging Face does not complain. Okay, now we have the input IDs. This is the prompt, just tokenized. And let me have the textual version of this as well, just store it. Maybe we need it sometime when we want to log the examples. Let's decode this. Add a special tokens. Skip special tokens. I don't want to skip this because I want to see them actually. And there is also a flag, clean up tokenization spaces.
Right?
Oh yes, sorry. Clean up tokenization spaces, this flag. I'm not sure at this point whether it does something, but sometimes the tokenizer remove or add some spaces or a new line. So I'm just fine to make sure that I disable that. Yes, so now that we have these two things, I think we are good with the processor example. We just return them. Input IDs, input IDs, and prompt is also equal to prompt. Okay, and this is an additive process. It's not going to modify the example in place. This is going to return this, and this kind of new dictionary is going to be used to update the original dictionary. So we don't have to pass the target or numbers. Okay, and so now that we have our function, let's use Hugging Face map preprocess example. This is our function and number of processes that it's going to use. Let's say it's 4. And yes, let's see what's going to happen. Yes, this is going to take a couple of minutes. We're going to cut that for you. Okay, so now the pre-processing is done. Let's check if the mapping is done correctly. So this is the first example. Let's print out the numbers and the target. Okay. So let's see if we have
It's prompt.
prompt here. Okay, perfect. So everything seems fine. We have the system message without the misspelling.
Yeah.
And we also have the numbers here and the actual target. And we have the examples also here. Okay, perfect. And as you can see, the prompt that kind of forces the model to start generating a response is pre-filled in the input as well. Okay. We can also, for a second, check the input IDs just to, I think it's also fun to look at them as well. Convert IDs to tokens. Okay, but yes. And these are actually by themselves a token. Yep.
Yeah, everything.
That's fine. Okay. Now I want to start implementing the reward functions or the symbolic checker or the verifiable reward, which is the other term that people use in the literature. So for R1-Zero, we are going to use particularly two reward functions, which is suggested from the R1-Zero paper, DeepSeek R1 paper. So here we are going to have particularly two rewards. So I'm showing you an example. So you have the prompt on the top, and then you have the entire model response on the bottom. Okay. And so we are going to have two rewards. So basically the format reward and the math or equation reward. Okay. And in the format reward, the function basically checks whether the response of the model is inside these opening and closing think tags. And also the answer comes right after closing of the thing, and it is also inside this closing and opening and closing of the answer tags. Okay. So just basically a simple format that we're going to enforce the model to follow. The reason that we need this format doesn't have anything to do with the particular reasoning behaviors. It's just to make our lives easy in a sense that we can easily extract the 45 number, the final answer from the model response, and then check it against the
You couldn't know where the
parameters.
answer is if the answer was not in the answer tag. It's
Exactly.
very hard to just find what part of it is.
Exactly, as you saw in the example that I'll show you with the 33 number that
Yeah.
we used DeepSeek R1.
There are many equations in there. And
There are many equations and many different approaches there. We need this to make our lives easy. And once you have this reward, we also have another reward here, the equation or math reward, which is the same that I showed you in the beginning of the video. It basically checks the final answer, which is extracted from these two tags, and basically checks it with the grand truth answer, which we know for this particular problem. Okay. Now let's start implementing the format reward function first, and then we go with the math reward.
But in our setting, we don't have a ground truth. It's just that it should evaluate to the target.
True.
Like we don't know the actual equation.
Yes.
Because there are many ways also.
In this task, we don't have a grand truth. So in a sense, our grand truth is a target number. We just check whether this, whatever is inside this, evaluate to the target number. However, in proper mathematical datasets, you always have a question, and then you have the final grand truth answer. And that's where the notion comes from. Okay, let's get it started. And we are now going to implement this. Before starting implementing the format reward, let me define the EOS token variable here, because our format reward is going to use that. And as I said before, the EOS token of the base model and the chat model of Qwen, they are different. So because we are using the base version, we have to make sure that we are reading the end of sentence token from the correct tokenizer. Okay, and so I'm going to load the original pre-trained model tokenizer here. We are not even going to make a reference for this. And let me just first extract the ID and then just make sure it is working. Perfect. And EOS and token itself is equal to to tokenizer and convert IDs to tokens. Okay. Okay. And just to give you a sense, what is the original tokenizer, the chat model tokenizer, end of sentence token? Yes, so as you can see, these two are different. This is for the chat version of the CLAN, and this is for the base version of the CLAN. We are not going to use this. Just create a copy of this token here so that we can use it later in the code base, okay? So let me delete this. Okay, now I want to define the format reward function. We are not going to see the entire implementation, the process to implement this function together, because it's boilerplate and it's not really interesting. Yes. So now I have copy pasted this chunk of code here. Let me import the regex. And okay, first I will go over this function. I will explain different parts of this. And then I think the best way to learn how this works is just go and play with it and just give it some examples, some output, and see where it works and where it doesn't. Okay, let's make sure that it doesn't complain. Perfect. And okay, the format reward function, it receives the completion, the model output, just a string, and it has to return a single number. The reason that we are not receiving the sample that was used to generate this completion, that we don't really need this here, because we are just checking the format. Definitely, we don't need to know the sample that was used to generate this. Okay, we are going to start from here. The reason that we add the think token to the completion is because we already added this to the prompt. Pre-filled it. We just added here to just make our regex matching convenient, but we don't really have to do this. And we make sure if the completion is ended with the end of sentence token, we just remove it, because as I said, the regex does not handle the end of sentence. And so the regex, I'm not going to explain this entire really big regex to you, but generally you can think of this as a part that checks the thinking tags. The think process open with this and close with this. There is no other additional think tags inside this. And you will see that the model also generates a lot of think tags, even inside the output think tags, right? Then it has to be followed by a \n, and then the answer is going to be inside these tags, okay? So the regex is defined as this. We can pass it to ChatGPT to see actually what are the exact part of this and how this works, but we are not going to focus on this for now. And we search for this regex here in the completion. If there is a match, if there is no match, we know that, well, the format is incorrect. And we just return 0. And if there is a match, we extract the content inside the answer. And here we just want to check whether the stuff inside the answer, it follows the format. Because sometimes the model actually puts the full equation, numbers with the addition, multiplication together, and it also says equal to the target. So we don't want that inside the answer tags.
Yeah, or it might use like other operations other than addition, subtraction. Maybe use factorials or something. We want to discourage that, right?
Yes.
That format is not allowed.
Yes. So if it's using some other character inside the tag, it receives a reward of 0.5. But if everything is correct, it is using only the allowed pattern, the allowed characters, we are good. It receives a reward of 1. And if any error happens during this entire process, it is going to receive a reward of 0.
I think in the original one, the reward 0.5 was also 0, but we found if you add it, it becomes smoother.
Yes.
So you want to give model something if it actually is it just conforming to the think and answer tag formats, but also another reward for getting the format inside the answer tags correct, to make it a little bit more granular.
Okay. And now we have defined this. Let's go and
check a few examples.
Let's run this together. So as you can see, it is returning 0. Why is this the case? We are seeing a starting think tag, which should not be the case, because the think tag, as we said, is already pre-filled in the prompt. So removing that, fix the issue, and fix the
That
problem.
one is correct.
Okay, and as you see here, the all of the operations and all of the digits, they all follow the allowed pattern. But let me check with some other characters here. And as you can see, we have followed the opening and closing of these tags, but the stuff inside the answer is not correct. It does not follow the allowed pattern, so it is going to receive a reward of 0.5. But removing that obviously fixes this.
Can you add a think tag inside this?
Yes. Yeah, so let's have some tag here and something in here. So as you can see, the regex checks for kind of nested tags, and it does not allow you.
What if we write something
after the answer tag? Let me.
Do you think?
It is. I think it is going to complain because the regex is going to force it to always end with the answer tag. But we can just check it here.
Okay,
Yes.
0.
Okay.
Nice.
All right. Now we know how the format reward function works, and let's go and implement the equation or math reward.
Right now we want to check with the target.
Okay. Now the time is for the equation reward or the math reward. I again copy paste a chunk of code that implements this. So it is the equation reward function. It receives the completion similar to format function. And in addition to completion, it also receives the numbers, the list of numbers which is inside the sample that was used to generate this example, and also the target number, just allows us to check the model's output equation. Okay, now let's see how it works. Again, we are adding the think tags here and just the completion. Although I think here is not that necessary to add this here.
Because you don't check it, right?
Yeah, we don't check this. So yeah, in your version, we can remove this. Or maybe we can remove this in the
maybe
in the production version of the code. Anyway, and since the reason that we don't check for the regex that we showed you before is that it is already checked in the format reward. So we just extract the answer part of this, and obviously there is no answer part inside the completion. The reward is 0. And once it is extracted, we just extract all of the numbers inside this equation, again with regex. And the reason we do this is just to check the only once equation, the condition of the format.
It should appear once and only.
Once and only once, right. So once we extracted used number inside the equation, we can just check whether it is only repeated once and it is the same as the input numbers. Okay. And once we have this, we again here check for the allowed pattern inside this equation. I don't think it is still necessary because we have done this in the format reward, right?
Yeah, not actually. The format reward it will be 0 if it's not respected, but also the equation reward should be 0.
The equation reward should be 0, exactly. Okay. So now we have that, and we make sure we only have subtraction, multiplication, everything. We can just use Python eval function to just run this equation.
Which is dangerous.
Which is dangerous. Probably you shouldn't be doing this. But with all the regexes that we implemented and also passing this kind of built-in functions as none, we should be safe enough for this
it's
case.
It's very rare. Unless someone provides you with a malicious model or something.
Yes. And yeah, so once we have the result of this equation, we just check it with the target. And if it is there is no difference between them, we just return 1, otherwise return 0. Okay, let's run this, no complaints. Okay, now let us check let us put some examples inside this function and see how it works. Okay, this is the example that I'm going to use. So the inputs or the input numbers are 1 and 2. In general, these datasets comes with at least 3 numbers, max 4 numbers, but this is just showcasing this. So we have 1 and 2, and the target is to produce 3. And so yes, we have this thing here. The model is outputting 5. So the equation reward is obviously equal to 0. If we remove this, it is going to be 3. And it doesn't matter whether this is true or not. It can be like 3 ones. It's still
0.
0. And yeah. And the reason for that is basically because of the only ones and only ones, right?
Yeah.
What else? Let us also check these dangerous
Yeah.
comments. I mean,
No,
this comment, this is not going to work obviously because it does not follow the allowed pattern. And also, even if for whatever reason that would pass, we have the built-in functions to be none, so these functions are not available there.
I mean, apparently I read from internet that you can access it in some twisted way. So it's not like a complete safeguard, but
yes,
it's not a sandbox. But
it is not a sandbox execution. For us, it's fine for this educational example, but obviously this is not a safe way of doing this. Is there anything else that we want to showcase?
I wonder what happens if you just provide 2 ones. Can like 2 ones and also like the inputs to 2 ones. Like the provided numbers are 1 and 1, and you need to create 3. No, 2. How can you create 2? Yeah, 2. Okay, this is correct. So it's okay with repeated numbers
if the
inputs are like
the inputs contain repeated numbers, but this is not going to be a case in the dataset.
Okay.
I don't think that we have repeated numbers inside the dataset. Okay. So just I'm going to revert it back to the original one. Yes.
So that's it. It's the task and the rewards.
So we have these 2 functions, format reward and the equation reward. So we are going to implement a function that just basically uses to create one single floating point or scalar for every completion.
So like you have a single reward.
A single reward function. So compute reward, completion, which is a string, and also the sample. The output is float. Okay, so the norms, as always, is sample norms, and target is equal to sample target. Okay, format reward is equal to format reward function. We just need to pass the completion, and equation reward is equal to equation reward function. We need to pass the completion, and we have to pass the norms and the target. Okay, so the output is going to be format plus equation reward. Okay, so this is a nice handy functions that combines these 2, and we are just going to use this function from now on to compute the reward of any
Can
completion.
you test it on the, let's just...
Yes, so let's have this, and I'm gonna use this one here. And I just need to create the sample for this. Norms equal to 1 and 2. Target equal to 3. Let's just run this. So
the reward is 2.
The reward is 2 because the equation match and also the reward match. So if I add think tag here, reward is going to be
1 because the equation matches, but the format doesn't.
The format doesn't.
What is inside the answer is actually correct, but the format is incorrect.
Yes.
Nice.
Okay. Hey, we are back. You might realize that our setup and our close slightly has changed, and the reason for that is basically we have lost our footage that we captured for the rest of this video. So we are re-recording. We pressed the record button and everything, but
and the application was working.
Yeah.
But it just recorded a blank screen.
Yes.
Every time. That's our fault. We didn't try to run a screen recording application, and that's why we need to record it again.
So we are starting from the episode generation part. And in the beginning of this video, I would like to give credit to the authors of these reward functions. We took these reward functions from the mini R1 repository, so make sure to check them out. This was really great starting point for us. Okay, so now that we are at the episode generation part, let me go back to this keynote presentation. And so previously we completed the reward computation, and now we are going to go back to the episode generation. Previously we did the thinking prompt and all prompt formation, and we discussed it in depth. And now we're going to take samples from the LLM and basically try to compute the GRPO advantages, use the reward functions that we implemented before, and basically create the entire generation pipeline for the GRPO algorithm. Okay, let's get started. So going back to the notebook, before starting, I want to discuss how in this code base we are going to take samples or generate from our LLM. And generally, if you are familiar with Hugging Face, then you have a causal LLM for language, like a Hugging Face model for causal language generation. You basically have a dot generation method, and it's basically you use this and you feed your prompt input IDs, and it generates the output for you. However, this method is not particularly fast, and in order for us to, because we are generating lots of episodes and in the entire duration of our training, we need something really fast. And there are multiple alternatives in the open source community, and for this project we are going to use vLLM. vLLM is an inference engine, and it takes your LLM, which is out of the shelf, and you import this vLLM into this inference engine, and you just take the samples from the vLLM. And this is done very efficiently. It manages the memory very well. It has very high throughput, and basically everything we need for this project. Other than vLLM, we have other projects such as SGLang and TGI. And I think to this moment, SGLang, it has a bit higher throughput from the benchmark that I remember. These frameworks, they always changing, and at some point, one of them is going to be better than the other.
At the right time that we wrote this, SGLang gave us some instability, so some CUDA illegal access error. That's why, like in the middle of training after 1 hour, so that's why we chose vLLM.
Yes,
I think their API is almost the same, so we can just
exactly. As I'm gonna explain in the next part, you're gonna see that working with this, even it is very similar to Hugging Face that generates. All of these, they're going to be very similar to each other, and hopefully they should be really easy to swap. But that's going to be the future versions of this code base if someone wants to do this.
Yes, it's very good.
Yeah, actually, as Milad said, we started with SGLang, and SGLang is, I think, about 30 to 50% faster than vLLM, at least in our setup. But as Milad said, vLLM is much more stable. We didn't encounter any out of memory or CUDA, random CUDA weird error. For the purpose of this talk and the purpose of this project, we are going to stick with vLLM. Okay, so let's just start importing it. The very first thing to do, we have two primary classes that we are going to deal with. The first one is LLM, and this is the starting point if you are going to use vLLM as a library. vLLM also has a command line interface. If you are going to use it in terminal, that's the one you're going to use. But right now, since we are using it in our Python code, that's the class. And also we have sampling params. I'm going to discuss this a bit later, but basically this controls the common parameters for sampling, like the max tokens and like top P, top K, the temperature, and so on. Okay, so now that we have the LLM class imported from the vLLM library, I want to first initialize vLLM and just play with it a bit and just explain the entire API and how it works, what it is going to output in your response, given your prompt. Okay, so let's get it started. So we are going to have the class, and Okay, this class is going to take a couple of parameters. I'm going to explain the most common ones. And so the first one that you are going to pass is basically the model name. So here you can actually input the path to your Hugging Face model as well. So either you have it in your Hugging Face repository, or you can actually have it in your local file system. So this string can be anything really. And the rest would be the GPU utilization memory, GPU memory utilization. I think this is before, like, this is one of the stuff that you're gonna control if you want to manage your memory. So for this project, since we are going to use single GPU and we are going to keep the model, the reference, and the optimizers, everything in a single GPU, we are going to only use 0.2 for vLLM. And given that we have a 80G GPU 800 large, this is going to be about 16 gigabytes, I think.
But it is just for the KV cache, right? Or is it also for the model?
That's a good question.
We can check.
Yeah, I think majority of the memory utilization for vLLM is just for the KV cache, because our language model is a 3 billion model, and if we imagine we have the BFlow version, which is the one that we're going to use right now, it's going to be about 6 gigabytes.
True.
6 or 7 gigabytes, I guess. Given that we have 16, the rest would be just hopefully the KV.
So after we initialize it, we check whether the consumption is 16 gigabytes or 22.
That's a
And we
good
will
point.
know. Let's see.
Okay, so the next parameters is basically the data type, the model data type. Generally, it's bfloat 16 because we have 800 GPUs, and these LLMs, they support, these GPUs support bfloat 16, so better to use them. Okay, next parameter.
One question I always have is the model is in bfloat 16 itself, right?
Yes.
So if you indicate here float 32, what happens?
I think maybe vLLM is going to outcast this.
Okay.
Yeah. So the next parameters, you may recognize that I'm reading from notes. These are the list of parameters, so I cannot really remember all of this. So the next one is swap space, and we are going to use very small one, so it's just 2 GB. And so what is the purpose of this swap space? So during the generation, one benefits of using this inference engine is that they use the memory really efficiently. So they are designed such that they are never going to be out of memory. They are never going to issue out of memory errors, almost. Even if there are no memory available in the KV cache, in the entire KV cache allocated for vLLM, it is going to evict some of the already generated responses, and either it just totally remove them and regenerate them again, or for this case, it's going to move them to CPU, like all of the KV cache computed for the responses that we are not generating in right now. They are just inside the KV cache if you are going to continue it. So basically, it is going to move those KV cache that are already computed to CPU, and it's going to hold it there, compute the generations for the current sequence that is running. And then once it's done, and if we are going to get that already generated sequence scheduled again, it is going to take those from the CPU memory and put it on the GPU again. Okay, but for us, because we have run this code before, we know that given that we have a limited maximum number of maximum sequence length, we are not going to encounter any out of memory issue. And so even if we assign very small swap space, we can, I think, I'm not sure whether passing 0 would work. Maybe it's gonna complain because it needs at least something. So yeah, we are going to use a very small amount of CPU memory because it's probably never going to happen that we are going to move stuff from GPU to CPU and then move it back again. So this is the swap space one. And there is another parameter, enable prefix caching. And we are going to set it to true. So what is prefix caching? So as you see, when you For instance, let's imagine that you have a chat conversation with an LLM. So the first 10 is yours, obviously, then LLM answers, then it is your turn, and so on, right? So during all of these generations that the LLM is performing, it is producing KV cache, obviously, right? And after the first turn of the assistant, it is returned back to you as a user, right? And now it is your turn to ask the second question, ask a follow-up question, right? Then once you ask this, the LLM is not going to recompute all of these history of your conversation again. So it is going to use it from the cache that it already holds for the entire conversation, and it's going to only continue generating from the new part of the data. Okay, and since we are going to generate multiple responses per each question, it's going to be beneficial for us to keep this option true, and basically it enables us to save memory and also have higher performance, because you're not going to recompute everything from scratch again for each new responses that they share the same prompt or same query. Okay, and the last part is max model length, if I'm not mistaken. So basically it says the maximum context size that vLLM is going to assume for this model, since all of our generations is going to be below the max number of tokens that we're going to generate for any prompts is going to be around 1024 tokens. We can just pass a simple number of 2048. And this is going to be more than enough, considering that we are going to have some tokens for the prompt. And yeah, you're going to be fine with this number. Okay, so let's run this. Oh, okay, now.
Maybe max model len?
Yes, probably. It's max model len. Yep, okay. So now it's going to load this model inside from Hugging Face. So this is the Qwen 2.53 billion base. You're not going to see the base here, but since it's not an instruct version, it's a base version. As you can see, it is using the Flash Attention backend because we have it already installed. It automatically switches to that backend. If you don't have it, I think it switches back to Triton backend, if I'm not mistaken. It's gonna take a few seconds to finish, and now, yeah, we are done. Okay, so the inference engine is now loaded and ready to be used inside the memory. Okay, how do we use this? It's actually very similar to how you approach using Hugging Face Generate. So we have another similar generate method, and you can generally pass your prompt as the first input argument to this method, and then you can pass your sampling params. So for now, let's just pass very simplistic prompts to this. So just remember, this is a pre-trained model, so it doesn't have any chat format, it doesn't know how to follow instruction and anything.
What is going to happen, you think?
I just want to pass hello world, and let's see what happens. Store the output inside each variable and see. Okay, so yeah, as you see, it's already generated. Let's see what it returned to us. So we have this is a list of request output objects. So request output object is kind of a class that vLLM construct when it wants to return the output to you. Since we have only a single prompt, the output is going to be the first item inside this list. You have this class, as I said. So this class, if you want to see the output of this, the actual output, there is this field .outputs. We're going to use that. Okay, and so we have also another list of completion outputs. The reason that it is a list here is because vLLM supports sampling multiple random responses from each prompt. Right now, since we didn't say you need to sample more than one, it is giving us a list that only has a single item. Okay, so we're gonna also get the first item, and to get the actual textual content, this is the text. Okay, so this is the text. Okay, so it says it was the first post on this blog I made, and I will use it.
That's it. It's very small.
It's very small, and the reason for that is because we did not pass the
Max token.
max token probably.
Oh, the default
is small. So and now I'm going to change these max new tokens, the amount of tokens that the vLLM is going to generate for us. As I said, there is these sampling params, and the way we are going to change this is by passing an instance of sampling param class. Okay. The parameters that controls the length of generation is max token. And for now, let's generate 200 tokens. So as you see, oh, it is actually fast enough.
Hello, so using Git. This is a hello across platform.
Yeah.
This is a hello across platform using Git. Okay, interesting.
Okay. Yeah. Okay, so now that we have this, we know how it works. I'm going to pass an example from our dataset to see what it returns, and perhaps we can see what is inside the initial distribution of this model at the pre-training point. Okay.
Can you also ask how the model feels? Hi, how are you? Oh, okay. Yeah, you can understand it. Okay.
Anyway, okay, I think we have defined the dataset variable. It is a Hugging Face dataset in the above cells. So as you can see, we have these fields, these columns inside this dataset. Let's take the first example, and I'm just gonna print the prompt here just to see what example we are dealing with. And yes, as we can see, we have these three numbers, and we have to create an equation that equals to 98. You have to use this kind of four operations, and we have to follow the format and so on. So you remember this from the part that we defined the class, okay, the data set, okay. So now I'm going to use this again, and as you saw, here is the place that you pass your inputs to vLLM. And as you can see here, it supports textual content, but in this project, we are going to pass the input IDs directly. And you can use both of these options, honestly. There is not so much difference. Performance-wise, the tokenization for these really short instances is not going to take that long. However, I think passing the input IDs, the prompt token IDs directly, it's just really beneficial for us in a sense that we can be really sure that the tokenization inside vLLM is not going to add or remove any special tokens or something unexpected that we have not predicted. Because at this point, when we are dealing with vLLM, it's a kind of a black box engine, and some of these behaviors, these edge cases, might not be that well documented. So it's just.
I don't think even we can pass, for example, turn off the add special tokens inside the vLLM.
Yes, I'm not sure how we should do this. Maybe there is an option.
It's just better to keep like passing input IDs, right? Then
Yes.
you're sure that.
So there is this, instead of just passing this as a positional argument, there is this prompt token IDs, and it takes you a list of lists, and each item of this list is going to be your token IDs. Okay, so we have the input IDs, which is the token IDs of our prompt for this example, and we're going to use this. So you see here that there is this line through this generate method, and the reason that you are seeing here is that I think the latest version of vLLM, they deprecated this prompt token IDs parameter. I think they changed it to something else. I don't remember it right now. For now, we can use this, but maybe in future when you are watching, this is not going to be available, but you can basically find the new input arguments for this method. But anyway, I don't think it's going to they are not going to change the behavior.
Yeah, for sure they support input IDs, right?
Yeah, they're going to support input IDs, at least from in the library form.
If it was me, I would stop the support for the string.
That's one option. Okay, And yeah, it's generating. Let me increase this to 1024 tokens just to make sure that we have enough space for the model to generate this. As you can see here, actually, this is not a bad output, to be honest, because it is totally related to achieve the target of 98 using numbers. As you can see, the model is repeating the numbers perfect. It is not like a totally random output. It
Very
makes sense.
close to solving a problem. Finally multiply the values.
Let's sample a couple more time. Sometimes you see funny outputs. Let's see if we have the luck with us.
There you go. Think. Okay. Oh, you already have a think token happening, but it's not in the format that you want. But
yes,
like
and
you shouldn't actually generate it.
Yeah, as you can see, you are already seeing the language switching phenomena that DeepSeek paper reported. Right now, it seems to be Chinese characters. I'm not sure, maybe.
No.
And it is not always Chinese. We have encountered Arabic and Persian characters, Persian alphabets. Like really anything could happen. I think even here, I'm not sure what language this is, but yeah, I don't know. Any case, so you see how the vLLM works. And the second option, I want to just finish this section with going over all of the samples of all of the arguments in the sampling params to see how we can control this. I think the next parameter that we are going to definitely use in this project is basically n. So what is n? It controls how many random independent generation vLLM is going to create for each prompt that you're passing. So if you set n equal to 2, you're going to receive 2 generations for this prompt. And if you have another prompt, basically you're going to see another 2 for them as well.
So it would be output 1, right?
Yes, exactly. The first item that we are assigning here, it is basically the list of the samples that we have passed. But the second in the index that we are passing is basically sorting through the generations.
The generations for that prompt.
For that particular prompt, exactly. So let's see. We have this one, and this is the first. The second one should be this one. Yes.
You're not bad. It's this answer is following our format, just the format.
The format almost, because the brackets, I don't think we support brackets.
Oh no, yeah, that's true. We don't support brackets, but I mean, it follows the think and answer format.
Yeah, it's really good actually in that sense.
Oh, funny. So having very good pre-trained base models really help.
Yeah, exactly. So we can change this.
I wonder what Llama would do here. Llama 3, like
Llama 2, even Llama 3, like 3.1 at least. And those are interesting cases.
Don't spoil it. You can try. Read the script.
Yeah,
that's a very good starting point.
Yeah, in this like textbooks, there are like parts or questions that try
that one yourself. Is left to the reader.
Yeah, this one is left for you. Let's sample 10 just to see a bunch more examples.
What token per second would be?
The throughput is about 500 tokens per second. However, remember that this is a small batch. 10 samples.
You can support much larger batch
size. Yes, if you increase the batch size, effective batch size of a vLLM, you're going to see much higher numbers. Second one, third one.
That was truncated. Let me think about the equation again. Oh, already you're seeing some interesting. You're already seeing some verification or something. So you see it in the samples of the pre-trained model.
Yeah. So any case, now we know basically how vLLM works and we know how to control it. And before finishing this, let me just go and check over the last parameters. So temperature, basically for us, I think it is 1.0, but you can obviously change this to anything you want. If you set it to 0, it is going to be greedy sampling.
Does vLLM have true greedy sampling? Like you sample again and it's the same thing?
I think for this example, you're going to run this, and I think you're going to see exactly the same output. However, because vLLM is doing dynamic batching, and there are examples coming from the scheduler to the inside of the GPU, like the entire computation in a dynamic way, there is a possibility that for each of these dynamic batch sizes, the underlying CUDA or the underlying torch implementation, they're going to use different kernels, CUDA kernels. And these different CUDA kernels, they are not necessarily going to give you deterministically the same answer. So you might see slight like variance when you even sample with
Good point. So
temperature
even with
0.1.
temperature 0, it all
Yes.
depends on your batch size or
Exactly.
like what
And
CUDA kernel is going to show.
you can sample with 0.2, but probably it is going to generate more garbage. Okay, so as you can see,
Yeah, it becomes very
is
bad. Very doesn't make sense.
we have other parameters, top k and top p. So I think the default value for top p is 1 and default value for top k is -1. And for this project, these two are going to be disabled. We are not going to use top p or top k sample. In the next part, we are going to implement the actual episode generation part. I would like to again go over this slide and just explain what does an episode really mean. And so the way a policy gradient algorithm work is through sampling generations from your model and using the reward to compute basically the words of every generation, and using these entire episodes to compute the gradient of policy with respect to gradient of the reward with respect to its parameters. And this is happening inside the loop. So you're going to sample again, compute the reward, use that to compute the gradient, estimate of the gradient, and again. Okay. So an episode basically is a set of query, the responses from the model, and the advantages. Okay. Intuitively, a policy gradient algorithm, it's going to increase the probability of high rewards responses, and it's going to decrease the probability of low reward responses, right? And these high or low rewards, they're going to be controlled by a variable called advantage and a concept called advantage. And GRPO is going to have its way of computing its advantage, but in general, this advantage controls how much a response is going to be preferred or dispreferred under the model distribution. And we are going to explain all of this in a more detail in the policy gradient section, but for now, just have this about what advantage really mean and what an episode is exactly. I want to show you plots of this entire episode generation components. So as you can see here, we have the prompts. So we have 2 prompts here, and for each prompt, we are generating 4 completions. So at the end, we are going to have 8 episodes. And once each completion is computed, we use the reward function that we defined before. We compute the reward as well. And with this reward, we compute their advantages. Okay, so what is an advantage here? In GRPO advantage, you can think of this advantage as essentially a normalized reward. And this normalization is happening among the responses to a single query. Okay, so that's the reason that you're seeing R minus mean divided by the standard deviation. So it's renormalizing these rewards to compute the advantages. However, you should remember that these advantages, they are computed for each responses, right? They are not computed for each token. This is computed only for each responses. GRPO in general doesn't have any fine credit assignment. And once these response advantages are computed, they are going to be repeated for every token. Okay, so all of the tokens inside this response are going to be treated equally. If we happen to know that this response is a high advantage response, we're going to increase the like prob of all of its tokens at the same time. Okay, the output of the episode generation component in this code base is going to be the query token IDs, the response token IDs for all of this, and the advantages. So as you can see, the length, so these advantages, they match the length of the generations, the length of the responses for each of these. Okay, now let's get back to the code. I want to first implement this all for a single example and just compute everything, and then we are going to introduce nicely implemented function. Okay, so I'm going to define a single sample here, and I'm going to use a very basic example that we have in the cells above. If I remember correctly, it was 1 and 2 as the input numbers, and we had a target of 3. And so this was the input of this example. Let me just tokenize this. So we had this pre-process function that we gave these as input. Let's see the output of this. Okay, perfect. So we have the token IDs and the prompts and everything. Okay, so just to show you what does this prompt look like. I'm sure you all know this, but this doesn't hurt. Okay, so this is the prompt, this is the input, and we have the target of 3. Okay, next I'm going to paste a couple of synthetic completions, and we're going to, instead of using vLLM for this, I'm going to just use those completions because for now it is a simplistic example just to see how this entire episode generation works. These are the completions that I just pasted. So as you can see, these completions are in token ID. They are not like in the string form. And the reason for this is that the vLLM is going to return these token IDs, not the entire like textual form. It's not going to detokenize this for us. Okay, I have pasted 4 generations for this, for synthetic generations, obviously, for this sample data, like data instance, and these token IDs, they correspond to these generations. Okay, and I would like to go over all of these completions just to see how do they look like and what are the rewards. Okay, the first one, as you can see, it's a good looking instance, like completion, because we are closing the think tag and we have everything inside the answer tags as well, and also stuff inside the answer is correct. Okay, and the second one, it does not get the format reward because there is an opening think tag inside the thinking part. So the reward for format is going to be 0 for this. However, as you can see, the answer part is correct, so it is going to receive a reward for the equation. And the second one, obviously we can see that this is not correct, so it's not going to receive a reward for this, but the format function seems good.
Yeah. Can you write the rewards that you expect?
For this,
Let's see.
So this is 1 plus 1. The first one is for the format, the second is for the equation. For the second one, we are going to receive a 0 for format, reward of 1 for the equation. This one, the format is fine, however, the answer is incorrect. And for this one, it's both the format is incorrect because it does not close the thinking tag, and also the answer is incorrect as well. So now that we know how this completion looks like, and these are the corresponding token IDs, and obviously once you have received this from vLLM, we have to convert them to a textual format. Okay, so I'm going to define a variable called responses, and I'm going to use the tokenizer. There is this batch decode function that receives the list of token IDs for all of this, and it's going to generate the output for us. However, I want to specify some of the flags for the code. Basically, I want to set the skip special tokens to false, because sometimes it does have this option to remove the special tokens for you. I don't want to deal with that. I just don't want the tokenizer to do any kind of processing for us besides converting token IDs to the string form. And also there is a cleanup tokenization spaces that I would like to set it to false as well. Sometimes there are some weird phenomena happening with these tokenizers that after detokenization is done, it tries to do like removal of some spaces. However, I remember this was the case in the older LLMs, like for instance in T5 and so on. I'm not sure whether this is the case with Quen models, but let's just keep it for now. And okay, so let's look at the responses. Yes, as we can see, they all match the ones that we have here. One particular point is that we have not included end of tokens in this textual comment that I have written here, but in their actual completion token IDs, you can see that there is a end of sentence token ID. Okay, and the reason that we have included it here is that vLLM is going to include this for you in the outputs. Okay, since we have the textual form, we can easily go and compute the reward for all of these responses. So I'm
Let's
going
see if they match our expectation.
Yes. And so we have the compute reward function. It receives the completion. Let's define a response variable for this particular item. And it also received the sample. Okay.
Oh, where is the half then?
Where is the half? That's a good question. Maybe it's checking. Let me copy this and move it here.
Yeah, maybe just a compute format.
Yep. Let's see. So we have format reward function, and let's pass this.
Oops. Can you remove the thing tag and see what happens? Is it going to jump to 1 or? Oh.
Let's see. I think if the reject is not going to be matched, then it is always going to be 0.
But I think if you remove the thing, like this one, the first
the
one.
first one, yes, the first one is going to be
no, interesting.
1. Yeah. No.
So we only give the half if there's something inside this broken, maybe. Wait, can you? Yeah, put a. What is it? Okay, in this condition it becomes the half, but if the other part is broken, it gives this as 0.
Yeah. Any case,
you can fix it yourself. It's not broken. It's just.
Yeah, this is how it is defined for now. Okay.
Yeah.
Let's continue with episode generation. So imagine that these are reward functions that are defined. You can add yourself like another reward functions or anything. So the episode generation part, it does not really assume anything about the reward. So it assumes that you just pass the completion. It just receives a floating point, a single scalar number for each of these responses. Okay. So now that we have this, I'm gonna convert this to NumPy arrays. Just it is much more easier to work with NumPy arrays in this case. Okay. So now it's time to compute the advantages. And let me go back to the slides that we had and see how these advantages are computed. So as I said, we are going to renormalize these rewards. And this renormalization, as I said, it's happening inside this group of responses for prompts. And that's where the name actually comes from. GRPO, the group thingy, is from the group of responses to a single query.
Yeah. So in our example, it's just we have 4 completions per this single prompt.
Exactly. So we have a group of 4 responses, but this is a group for the single response, the sample that we define here. This one. So this basically constitutes our group. Anyway, so let's now move on and compute these kind of renormalized rewards, and we call them response advantages. I'm gonna use the NumPy functions. So we can actually use NumPy mean. We have to pass the rewards and just divide it by put this entire thing inside the parentheses, and let's divide it by the standard deviation of these rewards. Okay, and we're almost done. However, it's good to add some basically epsilons to make sure that we are not overflowing. Yep, and this basically constitute our advantages.
Yeah. The funny thing about GRPO is that by chance, even if your standard deviation is 0, it means all of your rewards are the same and the mean is also the same. So you have 0 also at the denominator is also 0. So you won't have problems.
Yeah.
But it's just by chance. Stay safe and use epsilons.
Yeah, the denominator is going to be 0. However, since Python is going to compute the denominator as well for you, you should have this. Yeah. this epsilon. Okay, so now let's look at these numbers, these advantage numbers. I think we just created these completions by chance, but I think their advantage is actually in a nice format, a nice result. Okay, and let's look at the rewards that we have here. So this is the one for the full response, everything format and like equation, everything checks out. The second and third one, they have one problem. One of them, they have an issue with the format. The other has an issue with the equation. And the fourth one, it doesn't have anything correct. Okay, so that's why we have it here. But as you can see, when you renormalize everything, the first one is going to have a positive advantage per se. And the last one is going to have a negative one because it's really a bad response. So the first one is really good because everything checks out. The last one, it's really bad because nothing really works. However, the two that are in the between, in the middle, they receive a weight of 0. So what it means that these two, they are not going to contribute to your gradient computation. And basically, this kind of represents the average response of these two represent the average response of the model to this question. And you really want to reward the stuff that are above this average, and you want to penalize the stuff that are below this average. So this is where the normalization really comes from. And okay, so now we have computed the responses for the advantages for the responses. But as I said, the policy gradient or the implementation that we have here, it receives advantages per tokens. Okay, and GRPO, it doesn't compute advantages per token particularly. However, it just copies the advantage for all of the tokens in response. Okay,
same advantage to all tokens.
Yes.
For response.
Exactly. So let's define the actual advantages, and we can say per token advantages, but I think in the oral terminology, always advantages are defined for each individual action, and actions here are just tokens, each individual tokens. Okay, so we are going to iterate over the responses and basically the response advantages. Okay, actually, I think it is the completions because the responses, they are just textual form. We need to define these per tokens. Okay, so let's just change this to that. And response advantages. Okay, so this is going to be basically response advantage times the length of completion. Okay, so just print this out. And as you can see, we have a list of 4 items, and each item is a list of advantages for the each response. And as you can see, all of the tokens inside the first advantage list is the same. This is the same for all of them. Okay, so if you just want to test this, you can see that the length of the completions at position 0 and the length of advantages at position 0, they all match. Okay. And now that we have completed this, we know how it is everything from the beginning, from the prompts to completions, and then to reward computation, to reward normalization, response advantages, and per token advantages is just completed. Let me go over a couple of examples for renormalized advantage, renormalized reward or response advantages, because I think intuitively, if you look at this example, it makes sense that what it is actually doing. So I'm going to copy paste a few examples and we are going to go over them. Okay, we have the first example, and as you can see, we have 5 rewards, and it means our group of responses, we have 5 responses. And so this is our rewards, and the first 2 are correct, and the second ones, the third, fourth, and the fifth one, they are incorrect. And just assuming that we have a binary reward function for these examples, and the 1 is equal to correct and the 0 represents the incorrect. Okay, and let's see the advantages. Here, as you can see, after the renormalizations, the only good stuff, the only good responses, they're going to receive a reward of, or weight of positive weight or positive advantage. And the rest that are incorrect, they're all going to be negatively discouraged. In this example, we only have only a single successful answer or response, and the rest are just completely incorrect. And you can imagine that this case represents like a more difficult question for the model, at least at the current iteration of our algorithm.
And you finally solve it once.
Yeah, it barely solves this question, and it happens to be that we have only a single response that is actually successful. And as you can see, the weight that is assigned to this single successful example is actually quite positive, right? It is much more positive than these unsuccessful, and even in these unsuccessful ones are negative, right? So the absolute value of this value that is assigned to the successful one is much more than the negative ones. And even comparing this with the previous one, we can see that it is encouraged even more, because it's a valuable example, because it means that probably you found the solution, the model found the solution, and you really want to take an advantage of it. The third example represented a hard question, and all of the responses, they are unsuccessful. And computing this, it means that, as you can see, the advantage is going to be also 0. So what it means is that these responses, they are not going to really affect your policy gradient, because on average, this model is really bad on this question. So there is really no
advantage to any of the responses.
There is no advantage or disadvantage, to be honest, to one of these responses.
They're just equally bad.
They are equally bad, yeah.
Nothing so you don't want to encourage or discourage any.
Yeah, nothing is really above or beyond the average. The next example is also similar, but in the opposite way. So here we have all of the responses for this particular problem. That is all correct. And this kind of represents a kind of an easy question for the model at this iteration. And as Mila said, there is no advantage to any of these. So all of these, they are going to be assigned a weight of 0. So none of this is going to attribute anything to the final gradient for this iteration, at least. Let's look at another one. So in this example, we have almost everything is correct, but we have one that is incorrect. This one is similar to the one that we saw here, but in the opposite way. So the correct ones, they're going to be encouraged, but the one that happened to be really bad, it's going to be
really punished.
I hope you folks understand this concept of renormalized advantage. Finally, I would like to I'm gonna copy paste the entire episode generation function from up to bottom. And this is a completely implemented function, and I'm just going to explain it line by line, but the entire steps inside this function, they all are the stuff that we just did here. Okay, so yes, this is the episode generation function. As you can see, create training episodes. So let's see first what it receives as input. Okay, so it receives the input samples, like the data sets or prompts that we actually use to generate these responses from vLLM. And we are going to receive all of the generations and also all finished results. I'm going to talk about the finished results in a bit, but I just want to explain what these two lists are. So the samples here, let's say we use 4 samples to generate the episodes for this training episode for this RL iteration. So the all generations list, it is going to be 4 times, let's say we had 5 per each, 5 responses generated per each prompt, and it's going to be a list of length 20, okay? And so these responses are going to be listed from the order of their prompts. So the first 5 are the generations corresponding to the first prompt. The second 5, they're going to be the generations of the second prompts, and so on.
And the other option was to make them a list of lists, but I think SGLang didn't return something like this.
Yes.
So we designed it.
Yeah, we designed it in this way, and I think you can go in both ways. However, we just want it to be compatible with SGLang. So if someone in the future wants to implement this, change vLLM to SGLang, they just don't have to change anything here. So what is the finished reasons? vLLM is going to stop generating of a response mainly in two different ways. So first, it's going to stop generating if it sees end of sentence token or any stop sequence that you pass to the LLM. So if it sees that, if it sees end of sentence or that particular list of tokens that we specify as stop, vLLM is going to stop generation, right? And the second way vLLM can stop generating is if it hits the maximum length.
And can we see it in one of the outputs? Maybe
Actually, I think
we
if
should
we
have it, right?
have, yes, I think this one. Let's print this again. Yeah, maybe I change something or 0.
Okay.
Yes, I think this is the response that we generated with temperature.
With a very high temperature.
With a very high temperature.
Most probably it doesn't have an end of sentence. End of statement.
Most likely. So if let's look at the output object for this one, and I think there is a field here, if I'm not mistaken.
Interesting. It's very long as well.
Yeah.
Stop reason.
Stop reason, exactly. I think the stop reason for this is none.
Is it none? How come?
Yeah.
Is it a function? No, this cannot be.
Yeah, it's a bit strange, to be honest. Let's reduce this generation length to, I don't know, 10. Token IDs.
Oh,
finish reason.
Answer reason is none. Interesting.
I think this is some sort of a backward compatible.
Maybe it's a placeholder for the actual keyword that has stopped the generation. No?
Maybe. So, any case, so we have the finish reason here, and as you can see, it is length. If it happened to be that it's just a stop because of like hitting any end of sentence expression or sequence, it is going to return as a stop here. So instead of length, it's going to be stop.
To stop.
Yeah.
I see.
It's just going to be a string that says a stop inside it. Okay. So yes, these all finish reasons, it is going to be a list of strings for the stop reasons of all of these generations.
So it's either length or stop.
Either length.
At least for vLLM.
For now, it is. Yeah. I think there are some cases if we stop by some sequence other than the end of sentence, I think there's going to be some option inside vLLM that it returns why it did stop.
Okay. But we are not using it.
Yeah. So as I said, these all finished reasons, it is going to be the same length as all generations. So it is going to be 4 times 5. It is going to be a list of 20 as well. Okay. So as an input, it's going to receive these 3 variables.
But can I ask a question? Like, why do we even have this? I think we are not using it, right?
We are not using...
But it can be used in the rewards, for example.
It can be used for the reward. And one of the... Like, in this case, it's not going to be used. But in some cases, when you're not extracting the final answer from these answer tags, for example, if the model is generating the final answer inside LaTeX boxed environment, box command, in that case, if the model has generated that, but it has not stopped generating, maybe it has hit the maximum tokens, but it hasn't finished its response, maybe it wanted to say a bit or wanted to explain its answer. In that case, you can decide whether you want to reward that or not reward that. Based on the finish reason. Based on the finish reason.
So you're saying, like, if you have the correct answer but you did not finish, I'm going to give you a reward of 1, or maybe you decide that no, you actually need to finish it.
You need to finish it. The most implementation that I see, and the implementation that we had in our code bases before, we are not going to give it a reward if it doesn't finish. And in some inference engines, I'm not sure whether this is the case with SGLang, if the model stops generating based on an end of sentence, there might be cases that it does not going to include that stop inside end of sentence token inside the generations.
I see, and you need to concatenate.
So you have to decide based on finish reason to whether you want to concatenate or not concatenate. Because if it has not finished the response, you should not really concatenate this by yourself.
Yeah, that makes sense.
Any case, not important for this. In all of the generations, vLLM is going to put end of sentence token if it reaches that inside all of these generations for us. So we don't have to worry about that. Okay. As you can see, let me also define these variables. Variable here, I think we use 4 here. In any case, and so there are some like kind of sanity checks. Length of all generation, it should be equal to length of all finished reasons, and also it should be equal to length of samples times the length times the generations per sample. Okay, so here we're going to just create indices for all of these groups of responses per each of these tokens. This is nothing really special, and we go over these groups and we extract their token IDs. We convert them to their textual format responses. We use the compute reward function to compute reward for each of these individual responses. And once we have them, we compute the advantages from the GRPO advantage formula. And once you have them, you just repeat them for every token. And basically, this constitutes your advantages. And finally, and for
up to this point, where it looks very close to what we are doing manually. So
exactly, just exactly the same thing.
I think it's just this part that is a little bit different.
Exactly. So here is we are going to append the result of these things to 3 different variables. So here is where the output of create training episode, output of these functions come into place.
Okay? It's the packaging.
Exactly. So the return of this is a dictionary, and this dictionary has 3 keys. Okay, it's going to have the query token IDs, which are the token IDs of the prompts, and the response token IDs, the token IDs of the generations, the completions, and the advantages for each of these individual responses. And the length of these advantages are going to match the length of the responses. Okay, so just one thing I want to mention that here, because the stuff that are outside of this function, they do not care about like individual or like different details in the episode generation. They only care about these particular episodes. And in those cases, we are going to repeat the prompts for each of these responses in each group. We know that for each of these responses, we use a single prompt, but since the outside code, they do not care about the different details in here, they just take episodes as inputs. We have to repeat these queries for each of these responses, obviously.
Each episode is a training episode, and maybe it's going to be chopped and sent to multiple nodes. Not in our code base, but
yes.
So
exactly. Yeah, so nothing really special. So as you can see here in the all query token IDs, we are just repeating the token IDs of our prompt 4 times the number of the length of our group. And for the token ID, for the response token IDs, we don't have to do this because already we have 4 of them, or generations per sample number of them. And the same goes for the advantages. Okay, so yeah,
we should be able to run this on our own.
Exactly. So what is our sample here? We have this sample. Okay. And
do you want to run the cell again, or are you sure that it's in the memory now?
For sure inside the memory. Okay. Any case, let's go and try to run this function. See what it returns. So create training episodes. As input, it receives samples. So we just pass a list of 1, which is our simple sample, and it receives the list of all of these generations. For us, it was the completion variable. And we didn't have any finish reason list, so we're going to just create stop times 4, or basically the length of generations. And this should do the job for us. Let's see. Yes, as you can see, I mean, it's quite a long query token IDs, but I think let's store this inside a variable so we can inspect it manually. So we have all advantages. And so if you remember from previous parts, this was the advantage of all of the tokens in the first response and so on. And the last response was obviously the bad one, so it had the negative advantages. And
Yeah,
which
so
is
they are the
implemented.
same values
They are the same values.
as
Yes.
we computed like in the notebook.
Yeah. And so I want to also look at this. Let me just print, I don't know, like 10 of them, I guess. So I just want to show you that this is the same values, same token IDs for all of these prompts, right? Second one, the same. For the third one, same. For the fourth one, the same. Oh, fourth one, the same as well. Okay, so I guess now we have the kind of the component inside our code base that generates the training episode for us. And the next part is going to be us using these episodes, these query token IDs, these response token IDs, and their advantages to estimate the policy gradient.
Let's go and implement the policy gradient.
This part is going to be about policy gradient computation. And before going into code, obviously, I would like to go over the slides that we have again. And just to recap what we had before, we did the implementation for reward computation, and we now have the entire pipeline for generating episodes. So once you have this episode, and remember, this entire loop is going to be repeated. This entire three components are going to be repeated inside the loop. So generate episodes, compute the reward, update the policy, again, generate the episodes with the new policy, and so on. So now we are at the part that we have generated all of our episodes and we want to compute the policy gradient. So what is the policy gradient? It is you want to compute the gradient of the expected reward with respect to model parameters. Or in simplest term, we want to update our policy to be better at solving this task. Once you have all of these episodes, we are going to use a particular form of objective function to compute a loss and compute the gradient with respect to loss, or backtracking through this to update the policy. Okay, and as we are using GRPO for the implementation in this code base, and GRPO uses PPO objective, PPO clip objective, similar to many other algorithms such as mine PPO and any any PPO based algorithms, basically. In the next few slides, I'm going to go over the PPO objectives, what it looks like, what does it really mean, and see the actual form that we are going to use. So the next few slides are not going to be particularly about GRPO. They're going to be about the PPO objective, but this is obviously the loss that GRPO uses. Okay, so this is the PPO clip objective. It looks scary in the first glance, but this is nothing really special. It is basically if and else implemented using mathematical operations. But let me go over it. We have one of the prominent terms here are the probability of the policy or your model for generating token Y or generating action at time step t, given all of the context that it has, the prompt and whatever it has generated so far. Okay, and we need this kind of probability from the current model and the old policy. What is the old policy? It is a policy from the previous auto iteration. Okay, so we know this ratio, and this ratio is repeated here as well. And we have this AT here and here. What is this AT? This is the advantage of generating token at time step t. So we have talked about advantages in the previous sections, and this is exactly like that. So if you remember, let me go back. These are the advantages that we computed before, right? And as we know, this is the same length at this as the completions. And now you can see the reason why, because all of these ratios, all of these probabilities, are going to be multiplied by their advantage. Okay, this is the advantage, and we have the clip and the sigmoid and the minimum. And I'm not going to explain all the details of this PPO objective. If you want to know about this, please visit, there are so many courses on RL, Sergey Levin course, OpenAI spinning up course. There are so many great resources. And I think intuitively, if you want to think about PPO objective, it creates a trust region over the previous policy. And if we are inside this trust region, we are going to receive the gradient here is going to be activated. If we are outside of this trust region, there is no gradient for us. Okay, so intuitively, we just want to update the policy when we know that we are in a kind of a safe region to do this. We don't want to deviate so much from the kind of old policy, and that's why we are doing this. And remember, this PPO clip objective, it does not prevent you from going too far, but basically if you're too
Does
far,
not reward.
yeah, it's exactly. But if you are too far, it is not going to be giving you any
Gradient, yeah.
exactly. So now that we know like a kind of a general view of PPO objective, I have a good news for you. We are not going to use this exactly. As I said, we generate episodes and we use this objective to compute a loss, and we use a backprop through this objective to compute the gradient. And generally, the way we do this is that for a set of episodes that we generate, we do a few gradient updates, often more than one gradient updates using this objective on the same set of episodes. Okay, and let's say you generate the episode and you apply 4 gradient updates. You compute this objective 4 times using 4 batches of random samples of your episodes, and you compute the gradient 4 times. You update your policy 4 times as well. Okay, this is how generally stuff are implemented. If you go to different code bases, you're probably going to see this. However, for this implementation, we are only going to update our policy once per episode's generations. Okay, so we generate, let's say, 100 episodes. We compute the gradient, we compute the loss on all of these 100 episodes, and we compute the gradient only once and apply it only once. Okay, once the gradient is applied, we update the policy, we go generate the episodes again, and do all of this stuff again and again.
In other terms, our data is always on policy now.
Yes, in terms of like
off policy is where you're training on data that is sampled from the not your current policy. So if you do multiple updates, as soon as you do a single gradient update, the trajectories that you have are no longer sampled from the current policy. But in our case, it's just we sample once, we take a single gradient step, we sample again, we take a single gradient step.
Yes, and one good result of this thing that we are doing is that many of the stuff that you're going to see here, they simplify. Okay, so what do I mean by this? As I said, the old policy here means the policy at the previous iteration, the policy that we used to sample the episodes, right? And since we are doing a single update, whenever we compute this objective, this pie of data, it has not updated yet, right? So it means that this entire ratio, it is going to be equal to
just
1, right? And so the good news here is that if you want to clip something that is already 1 with these epsilons, so this clip function, it is going to return this term, but just a ratio, right? There's not going to be any clipping, right? So this entire clip is going to be equal to this ratio, right? This ratio times the advantage, okay? And looking at the other term here as the input of the minimum function, we see that, again, ratio times this advantage, okay? And so obviously we have a minimum of exactly the same terms, and the minimum of exactly the same terms, we're going to be that term.
Those terms.
One of those terms, right? If we simplify all of these things, as we said, we are going to have this objective, okay? And this objective, and what would happen is basically if we take the gradient with respect to this particular objective, this simplified form, we are going to reach this form, and this form is basically vanilla policy gradient with advantage. And
it's just so obvious that it results in this, right?
If
you just eyeball it.
But if you're like me and it is not very obvious to you, we are going to have a proof of this, how you get from here to here, in the next section.
So here is a simple proof on why the PPO objective actually boils down to vanilla policy gradient when the policy is not updated and the old policy is the same. So the objective is the p theta over the p theta old multiplied by the advantage. And we want to take the gradient of this expectation. So what we do is we write it as an integration. So it would be, the expectation is over pi theta, so it would be pi theta multiplied by pi theta divided by pi theta old multiplied by the advantage. So as you notice, it would be pi theta to the power of 2 divided by pi theta old multiplied by the advantage. When the grad operator enters the inside of the integral, so it would be the grad theta of pi theta 2 multiplied by pi theta old multiplied by the advantage. But as you can see, this term and this term are not differentiable with respect to theta. So what happens is that we'll have just the grad theta of pi theta 2 divided by pi theta old multiplied by the advantage. So at the end, it would be 2 times pi theta multiplied by the grad theta of pi theta divided by pi theta old multiplied by advantage. So because the theta old and theta are the same, this equals to 1. So what happens, so it's like it's 1. So what happens, we will have here 2 times the grad theta of pi theta multiplied by advantage. And this is just where we're going to use the like trick. So what we do is we multiply pi theta and divide by pi theta. So this thing actually just equals to 1. It's just to transform it to an expectation. And we know this thing actually just equals to grad of log probability. So it would be 2 integral of pi theta grad theta of the log pi theta multiplied by the advantage. And this is just the expectation. So it becomes 2 times the expectation over grad of log pi theta multiplied by the advantages. And this is just the vanilla policy gradient. So as you can see, the gradient of this objective is just 2 times the vanilla policy gradient objective. And that is the
Any case, so we have this, so the gradient of this PPO objective, this simplified objective, is going to be two times this expectation, okay? And these two, we can safely ignore it because it does not change the direction of gradient, and it's always 2 in all of these things, all of these gradient terms, okay? So just I want to explain what does this really means. It means that we are going to compute the log prob of every generated tokens, and we are going to multiply them by the advantage that we know for all of these responses. And once we have this last term, we can just simply backprop through them, and the gradient is going to be computed. And if you have a batch of this, obviously you're going to estimate this expectation with Monte Carlo samples, basically, or the Monte Carlo estimation of this expectation. Any case, so this is a part of this PPO objective, but this is not the entire objective that we use in GRPO. And the second part is this KL form. So this KL, the job of this KL is to prevent us from moving too far from the reference policy. And the reference policy here is the policy that we started our training with. In this case would be the pre-trained model without any training, just the base version, right? And so how do we compute this KL term? In the recent versions of the RL code bases and in GRPO, we have this term which computes these different ratios and use them to compute the KL, and we backprop through this. I'm not going through too much details of how did we come up with this term, because it's really not really the focus of this video. But this expression, it's an unbiased low variance estimation of KL, which John Schulman, I think came up with this or introduced this, I think in 2020. So if you want to, you can go to blog post, I guess. So approximated KL divergence from John Schulman, and we are using basically K K3 or this form of the KL estimator. In any case, as you can see, the bias is 0 and it has lower variance than the first version. In any case, as I said, this is not the focus of this video. If you are interested, read this blog post. It's quite interesting. Let's continue. And before going through the actual implementation, I would like to discuss one more time what is the actual difference between GRPO and other algorithms such as PPO and WINE-PPO. As I said in the beginning of this section, the objective that we use to update the model to compute the gradients in all of these algorithms, they are all the same. However, the difference lies in how the advantage is computed in all of these algorithms. GRPO, by design, assign the same advantage, treats all the tokens equally, but algorithms such as PPO or WINE-PPO, they have fine-grained credit assignments. They actually compute per token advantages that can differ from different tokens in a single response. So if I were to visualize this, so this could be the GRPO, and these actions are different tokens generated for your response. And these are basically the gradients that you computed, let's say, for all of these generations. And if this is a positive or high reward or high advantage response, all of these tokens, they are going to be equally contributing to the gradients coming from this response. And if this is not a very good response, all of these tokens, again, they contribute to updating the model. But we can start to see the potential problems here, right? For instance, if everything up to this point, every part of the generation to this point was correct, and only the model just stumbled upon of a mathematical mistake or just miscompute something, and everything just goes off track after this point, all of these, even the first few parts that were objectively correct, they're going to be all discouraged, or they're going to be, the probability of those are going to be decreased all at the same time. As I said, these two, the other variants of algorithms, it's fine-grained credit assignment. They compute per step advantages and per step or per token advantages. And they play different contribution into the final gradient. So for instance, this A5, it does not really have any advantage. So its term is not going to be involved in gradient computation. And some we go in the direction of increasing them. Some of them we just go in the reverse direction. We just go decrease their probability. And generally the problem of credit assignment, knowing which of these tokens, which of them matter in the actual response, that's by itself is a kind of a very challenging and one of the core problems in even like classic RLs or entire RL, basically. Yeah, this is the overview of these algorithms.
I think like the way I see it is advantage as a technical term, I mean, as a definition, which is the expected return after you take an action and if you follow your policy, subtracted by the expected return if you just sample from the policy, like not fixate on that specific action. And these algorithms, they try to estimate that advantage. And GRPO's estimation is just very biased because different tokens should have different actual advantages, but they assign the same advantage to every token. But algorithms like PPO and WINE-PPO, they try to estimate the actual advantage, so it becomes fine-grained. So the way I see it is like just the advantages that they estimate is incorrect, is biased.
Is biased, yeah.
But bias is a term to just say it's incorrect, right?
Definitely. Yeah, this is, as Milad said, these are technical RL terms, and we are just going over them in a slightly hand-baby form. But if you are interested, please go ahead and just learn about all of these things.